today I want to wrap up with cycles. So we'll finish the cycle topic, and the remaining 3 lectures from tomorrow to Thursday, we will cover about trees, embedding boundary degree trees in random graphs. So this will be the cycle and tree topic. I want to start by recalling last week we proved a little bit technical lemma of finding large induced expander in the random graph, in the pseudo random graph. So let's recall. The first thing I want to recall is the consequence of Cauchy's rotation extension sprinkling technique. So first thing is lemma 412. This is a couple of lectures ago. It says that if we have a graph H, which is 2n/5 expander, okay, on the same vertex set as the random graph, okay, and we have then we sprinkle linear amount of edges in N on H, then almost surely we sprinkle G on top of the expander H0, then almost surely this is Hamiltonian. So now if we want to find the long cycle or Hamiltonian cycle even, we just need to reserve linear amount of edges first, which is this Gn 500/n. You set it aside, you will sprinkle it afterwards, right? You first, in the majority part of the random graph, find the large 2n/5 expander, which is this H0. Then we do this multi-round exposure, the sprinkling. So that means this makes lemma 414 meaningful, which is defined informally, is to find a large 2n/5 expander. So this is pseudo-random implies large expander, which can be combined with lemma 412 to find long cycles. Okay, let me quickly write down what it is. We have some integers, and I will write a shorter version because we have the formal version last time. Right, you have some MD, which are integers, and S is the set of low degree vertices, where the degree is less than D. Okay, these are supposed to be the small degree vertices. So then we have X, which is number of degree at most 1 vertices, where Y is the number of S ring, which are paths or cycles of length at most 4, either based on S with endpoints or intersecting S, such that X plus Y, 7Y is not large, and number of S ring is small, bounded by this S. So this is basically saying that there are few vertices of small degree and they are mostly far apart. Okay. The second condition is large set expansion. It says that for any A, where A is of size M, then you reach lots of vertices, 4n/5, large set expansion. Last one is upper uniformity. There's no dense patch for any A in V of G, where you're not too big. Then number of edges induced on A is less than dA/100. If these are satisfied, then we can find a W of size small, which is measured by the number of low vertices of degree at most 1 and number of S rings. such that G minus W is the expander we want. Okay. Good. So we will do two things today. First, we will see that how these two lemma quickly implies two significant improvements of the results we see before. And second thing we will do is we will see yet another different technique rather than edge sprinkling, a conditioning argument to give further optimal improvements that will wrap up for the cycle topic. So first is long cycle and Hamiltonicity, part 1. Okay, we will use these two theorems, 412 and 414, to prove that first, how long a cycle we can find in GNC over N, linear number of edges, almost surely has a cycle CL, well, L is at least of length 1 minus e to the some error term based on C times N. Okay. So this is roughly, it looks a little bit complicated. If you ignore the little o1 term, this is roughly error term N over e to the C, basically. Okay. If you ignore the error term, which is a big improvement. Before we only have polynomial in C in the error term, 1 over C, something like that. And 416, originally due to Bolobash and independently Coleman's and Samarati, which says that GMP almost surely Hamiltonian if P equals to a little bit bigger than log n plus log n over n. Here, omega 1 is with respect to n. Some function goes to infinity with respect to n. Can be arbitrarily slow. Just a quick remark that if you change this plus, if you have same probability but minus omega 1, okay, then almost surely you will have, there exists a vertex of degree at most 2, at most 1. So this is the same probability threshold for minimum degree at least 2. The two coincide. This is why this is it's quite sharp. For both of these two results, they basically prove it's very similar. First of all, we will prepare it to fit in 412 for the sprinkling. We're going to split out this a little bit first, right? So for both, we consider this G with appropriate P to be union of Gn 500 over N union Gn P minus this, right? You split out a little bit for this guy to do the sprinkling afterwards. And all we need to do now is to find an expander here, right? Using lemma 414. If we can find a large expander using lemma 414, then lemma 412 tells us that with this sprinkling here, we can get a long cycle. All right. This basically is implied by, so this blue part is implied by the following lemma. 417. We let C to be large, okay, and P to be this threshold up there. then almost surely we have that GNC over N has a 2N over 5 expander of order 1 minus the same error term. Okay. The second one is GMP itself. So we have a spanning expander with all the vertices. So you see, 417 together with the two lemma we established before, or actually just with 412 is enough. 417 with 412, right? So this yellow part here, by the first part, we have a expander of this size. Then you do the sprinkling, the expander of this size becomes Hamiltonian. We get a long cycle of that length. And the second one, the whole random graph itself is expander. So if you do a sprinkling afterwards, the blue part here, we make it Hamiltonian. Okay. The proof of 417 make use of 414. So the goal now, as written here, the blue part, is to prove lemma 417 to find the large expander. To find large expander by 414, we know that all we need to do is to bound x and y. Well, also to prove the second and third condition, the large set expansion and upper uniformity, but this is quite easy. All these three conditions are fairly easy to verify. Let me write it down. Right? If it can bound x and y and prove the two pseudo-randomness property later, then W is small, we find what we need. In particular, for the second part, the Hamiltonian part, GMP itself is the expander. We need to prove that almost surely x and y, they equal to 0. You don't have vertices of degree m-1, you don't have S rings at all, right? Then that will be enough. So let me write it down. So let's first verify these two conditions. These two conditions has very low threshold to be satisfied. So it's quite easy. You see that our threshold here, we have two theorems. One is above some large constant over n. The other one is above log n over n. So proposition 418, this gives us the large set expansion and upper uniformity. So let's see, not too large, but large. Okay. Our P will be this large constant C over N. So this seems like a strange way to write it. So basically P is between 2 log N over N and below bounded by some large constant over N. Okay, maybe this is more natural. And we take M to be linear in N, very tiny, but linear in N. Then almost surely GMP satisfies, okay, I don't want to write these two conditions. I will just say satisfy these two conditions, okay? I don't want to copy this again. So we have this condition that every M set, its external neighborhood is at least 80% of the vertex set. Every set up to size 10M, the edges induced from the small parts, not so many edges. Okay, satisfy these two conditions. Satisfy that condition. I don't see any point rewriting that. Okay. Except that I have to change these. Let me just You have to change this to the C A over 10 to the 5 because we don't have D there, we have C here, right? Okay. Then, okay, getting these two standard thing out of the way, all these I will leave as exercises. Basically, first, second moment, you check the expectation and then you check the concentration. So we get these two things out of the way. We just need to bound vertices of degree at most 1 and the number of S rings. Okay. In the linear case, we want to bound it to be small. In the case when P is log n over n, we want to prove that they are both 0 almost surely. So we don't need to remove anything to make it 2n over 5 expander. Okay. We do it separately. For linear case, we have let C be large, then GNC over N almost surely satisfy that at most 1 plus little o1. This means for every epsilon, when C is sufficiently large, we can write here 1 plus epsilon. Okay. So here you see, in GNC over N, the expected degree of every vertex is roughly C. So I define S to be the vertices whose degree is less than 1% of what's expected, less than C over 100. Then this proposition says that X and Y, they are both small. X, the number of vertices of degree at most 1, is at most the C e to the negative C times N, exponential decay with respect to C. And the number of S ring is even smaller, right? E to the negative 3/2 times C. So this is exponentially smaller in terms of C than the number of vertices of degree at most 1. Okay. Proposition 420. Now we deal with the case when P is log n. Let's say it's between log n and 2 log n. Then almost surely GMP has no S ring, where S is again V, the vertices of degree less than 100%, 1%, 100%, 1%. MP is the expected degree, right? Or n minus 1 times P to be precise. So here, 420 says that when P goes above log n over n, S ring almost surely do not even exist. So this is a good time to point out a remark that when P is above log n over n, the only obstruction to Hamiltonicity is not S ring anymore. Before there's two obstructions. We need to get a large expander. We need to remove vertices of degree at most 1. We need to remove S rings. But now there's no S rings. So the only obstruction is vertices of degree at most 1. A remark here is that, yeah, exactly as I said, after P bigger than log n over n, obstruction to Hamiltonicity is that its minimum degree at most 1. We have vertices of degree at most 1. So in fact, which we will not prove here, Bolobash proved that a heating time result. Basically, I would just write like this. So what I mean is that if you think of random graph as a random graph process, meaning that every edge you have a probability P, but imagining all these random edge count 1 at a time with probability P instead of 1 at a time. Then when you add it 1 by 1, the moment that the random graph have minimum degree at least 2 is the moment the graph becomes Hamiltonian. They have the same hitting time, roughly. I don't want to get into too much about this. Okay, then that's it. That's all I want to talk about for the proof of these two theorems, 415 and 416. We have all the Lego pieces here. You just need to put the right proposition together with 417 and 412. Okay, and these propositions are fairly standard to verify them. So, right. Now I want to talk about the last technique, which was by Lee and Sudokov using a conditional argument. How can we possibly improve these two theorems further? These two. Okay. We want to improve these two further. Well, first thing is that here there's in exponent here, there's a 1 minus theta over 1. We will remove this exponential error. This first thing we will see. The second one is to improve this further, we will get it even more precise. Instead of little omega 1, something goes to infinity, we give some c there, which could go to infinity or could be a constant. Let me write it down. Okay, the first one is by Alan Fries. First proved by him. So both of these two were followed by a fairly short and elegant conditioning argument. Shows that GNC over N has almost surely, of course, has a cycle CL, where the cycle is of length at least 1 minus okay, compared to before, what happened to before? Let me write it here. Before we have the error term here, it's actually e to the, okay, we remove the exponential error, obtain the asymptotic form. It should be a capital C in front of e to the negative c with something 1 plus little 1. So it's a really, really precise form. This is the best possible form, basically. The long cycle. What about the other results? 423. First proved by I-type convolution similarity. We let P to be log n plus log n plus C, but C could be a constant, could be a function of n. Let's just write C of n, okay? Then, and let's let a little c to be constant, some real. Then we have the following. The probability that GMP is Hamiltonian goes to 0 if C of n goes to negative infinity. This we've already known, right? Because when C of n goes to negative infinity, this is minus little omega of 1, then almost surely there's a vertex degree at most 1. And goes to 1 if C of n goes to infinity. That means C of n is little omega of 1. That we've also just seen. This is the previous theorem we proved here, theorem 416. So the more precise form is that not just we can capture when they both goes to plus or minus infinity, we can also capture if it tends to some constant c, okay, this constant c that we set up at the beginning. Then the probability is e to the negative c, quite precise. Okay. These are the two final forms of improvement. We will sketch a proof. How do you do these two in a unified approach? Okay, so we present a proof using a conditional argument. By Lee and Sudokov. The idea is, can again be captured in one sentence. Okay, the idea is that, okay, before what did we do? Before we say, we do it in two steps. We first find in GMP a large expander. Then we use the Poch's rotation extension sprinkling. We sprinkle a little bit on top and to make it Hamiltonian. This is what we do before. Now we will skip the sprinkling part. All we need to do is to find the large expander, but we want this expander to be sparse. Okay, so the idea is that if a 2n/5 expander, let's call it H, inside GMP, before we find it to be large, right? Now, instead of finding a large one, we impose additional condition. We don't want it just to be large, but also sparse. This color is not so ideal. I want to is sparse. Then, in fact, if we look at the GMP on top of this sparse expander, it's already Hamiltonian, almost sure. Okay, so the difference is that, once again, I want to emphasize the difference. Before, what we do is we find a large expander, and then we do sprinkling. Now we don't do sprinkling at all. We just do expander, we find an expander, but in addition, we want it to be sparse. If it is sparse, then on top of this expander, the random graph is Hamiltonian. Okay, that's the idea. Let me write this down more precisely. This is lemma. Okay, in the precise form, lemma 424. It says that let's let P to be not so small, at least linear in the reciprocal of n, some large constant over n, and for any 2n/5 expander H in GMP, okay, if it is sparse, meaning that it has the number of edges is Pn²/10⁴. Okay, so the expected number of edges is Pn²/2, roughly. There are n²/2 pairs, and would probably be P. So this is saying that it's less than, say, 0.1%. It's sparse, but still constant proportion. It's less than some constant proportion of the size. Then, almost surely, GMP has a booster for H. Okay, has a booster for H. Recall that a booster is something that you can add to H to increase the length of the longest path until the graph becomes Hamiltonian. So in particular, if you add n boosters iteratively, then you can make the graph Hamiltonian. So all we need to prove is the first one. When it's sparse, you have a booster. Because then if this is true, consequently, we just make it even a little bit sparser, right? This is because we make it a little bit even sparser. Then by the first part, GMP has a booster for it. We add to it. Again, we only add one edge. So it's again sparse. By the first part, it has a booster. You keep adding it. You add at most n edges. And Pn squared over 10 to the 5 is larger than n by our lower bound on P. So you never go too dense when you add these n edges. The expander remains sparse after adding all these boosters until it becomes Hamiltonian, and that's it. Okay. So let's take a moment. Once again, all we need to prove is this one. Okay. When the expander is in addition sparse, then the random graph contains a booster for it. And how are we going to use it? Later, basically this reduces the task, all this improvement. Before our main task is to find a large expander, modulo all those lemmas we've already proved. But now our task, if assuming 424, is to find a large expander. In addition, it's sparse, and we want it to be sparse. This is also not so hard. I will give a sketch of the proof later. Basically, now if I capture it in one sentence, is that you basically sparsening the random graph, and then you find an expander there. After you sparsening it, then of course the expander you found is also sparse. Okay. Now, let's first prove 424 at least rigorously, and then we see its implication for the improvement. So the core of this method, giving these two improvements, is this lemma 424. So let me not keep writing 10 to the negative 4. We need to prove these first bullet points. Let me just let delta to be 10 to the negative 4. Okay. And we want to show that every expander with at most delta p n square edges, GMP has a booster for it. So let's call this family, let's define script H to be the collection of all sparse expanders on vertex set n, on the same vertex set, with E of H less than 10 to the 4, 10 to the negative 4 Pn squared. Okay, the sparse expanders. So then, after setting this notation, simply by union bound, it suffices to show, we just need to show that the sum of H in script H, the probability that we have H as a subgraph of G, or GMP. Okay, there exists a sparse expander in GMP. Meanwhile, and G has no booster for H tends to 0, right? Okay, what do we want to prove? We want to prove for any sparse expander H, G has a booster. So if you take the contrapositive, that means there exists one that G has no booster for it. What does it mean? This is exactly what's in the parentheses here. There exists one, H is in G, and G has no booster for it, the second event. Then we take the union bound, which is overkill, but anyway, we'll prove that that's little O of 1. That's enough. Okay? So to bound this sum, which is also easy, once you know the idea, it's not so hard, but the idea is nice. Let's define give some notations. To bound this sum, let's define for each sparse expander, we define B of H to be the set of boosters for H. It's a set of pairs, right? Adding which increase the length of the longest path. The set of boosters of H, set of boosters. The set of oh, similar thing happened before. I choose this pen, you give me another pen, which is strange. Is it okay now? Right, so the set of boosters of for H, okay, but that are not in E of H, okay? We want a set of boosters that's not already edges of H. This is for independence, you will see later. We define this, and right. Recall lemma 411, which probably you don't remember. Basically, Poch's rotation tells us what? It gives you lots of possible starting points. It gives you quadratic number of pairs in n, adding which it gives you longer path. It's booster. Quadratic in n meaning boosters, right? So it says that our booster is of size, at least n squared over 50 boosters. But since we choose those not edges of H, so we have minus, we have to subtract E of H, right? We don't want those in E of H. This is not a problem because E of H, this is where we use the fact that H is sparse. We still have lots of boosters, not edges of H. Okay, so this is at least n squared over 100. Now, let's define I sub H. I means inclusion, okay, to be the events that this particular H is a subset of G, is a subgraph of G. And define N of H, this means N means no booster, okay, to be the event that there's no booster, meaning that B of H, this special set of booster, not in E of H, does not intersect our random graph. Okay, random graph does not have any booster from this special set B of H. Then look at this probability here. It translates in this notation. So we need to show that the sum of H in script H, the probability that IH and NH inclusion happens, and if H is in G, then no booster also happens, this probability goes to 0, right? But for this probability, let's use conditional probability. This is So just look at the first line. This one almost the same, right? Except that this is a subset event, n sub h. We just need b sub h disjoint from E of g. So it suffices to prove this now. Okay, here's why it justifies the independence need, the need of independence, the choice of b of h. Note that n sub h and I sub h, they are independent events. Look again, I sub h is the inclusion, h is a subgraph of g. That it's only relevant to the edges in h, E of h, right? E of h are relevant here. And the events n sub h, the relevant edges are b sub h, which is disjoint from E of h. So whether or not G, the random graph, has edges in the set disjoint from E of h is independent of the I of h events. So this means we just need to prove we can get rid of this conditioning part, right? Implies that the probability that the conditional probability, we can get rid of the conditional part, just have the no booster events. But what is no booster event? That means none of the p probability inclusion happens for every edges, for every boosters, right? None of them is included in GMP. And we also know that b of h, there are lots of them, n squared over 100. So it's at most 1 minus p, n squared over 100, which let me just write it as e to the negative p n squared over 100. Okay. So then this implies that the sum that we need, we have the sum of h in script h is at most, we can extract this part first. We bound this uniformly by e to the negative pn squared over 100. Times the sum of h in script h, probability of I sub h. Okay, but what is the second one? The inclusion probability is also easy to estimate. This is at most. Let's copy down the first term. The inclusion probability, we know that each graph in script h has edges between 0 and delta pn squared, right? Then I have to choose n between, among n choose 2 positions, let me just write n squared, I of them to be our edges of the h. Then they all have to be included in random graph. So this is a crude upper bound, which is enough. This basically is the math part. The remaining is calculation, becomes 1. I will skip the calculation. Okay. So let's come back here. Apart from this calculation, the proof is really short, right? It's really short. All we need to, the essential idea, as you can see here, is to just define this booster disjoint from E of h to get an independence, which help us to write this joint event as just 2 independent events, and you can calculate it separately. But all in all, the idea is, again, this one sentence up here. If we have n over 5x, if we have an expander, and if it's sparse, then the random graph on top of that is Hamiltonian, almost surely. That's the idea. Okay. This saves us from doing the sprinkling. Now, good. Fine. This tells us that if we have a sparse expander, then on top of that, the GMP is Hamiltonian. How do we use it to prove 422 and 423? Okay, keep this lemma 424 in mind. Right. So if you stare at 424, this lemma, and stare at these two theorems, all we need to do now, both these two theorems, is to find long cycle. In particular, the second one, to find Hamiltonian cycle. So if you look at 424, all we need to do now is to find the H in GMP such that it's an expander, it's large, and it's sparse. Then we can use this theorem to prove that it's Hamiltonian. That's it. Okay. Lemma 424 reduce the problem of finding long cycles in GMP to finding large and sparse expander in GMP, right? This is the, and to do that, the following lemma will do that for us. 425. I want you to compare this lemma to lemma 414. Okay, these two are basically similar lemma. Different strength. One is this sparse conditioning argument, the other one is the sprinkling argument. So let me write down this lemma. Let's see, be large, and we have P between linear and not too large, 2 log n over n. Okay, and we take G as GMP. Right. We set our small degree vertices as usual to be those with 1% degree of expected. And we define x, the random variable, to be number of vertices of degree at most 1. Looks familiar, right? We are trying to find large expanders. So we have to delete vertices of degree at most 1. We have to delete this S ring, similar process in G. Okay, conclusion is that almost surely G has a 2n over 5 expander H of order such that H is large. Okay, similar as in lemma 414, but now we want it to be sparse as well, so we can achieve that. The only difference here is that we can also find it to be sparse compared to 414. E of H is at most Pn squared over 10 to the 5. Okay, if this is true, then we can invoke this lemma 424 up here. Our H is sparse, then on top of that, the random graph is Hamiltonian. Okay. Now, what do I do now? Right, a sketch of the proof. Maybe I will not prove it rigorously. I give a sketch of the proof. It's quite intuitive. Okay. Basically, let me draw a picture. Maybe that's more intuitive. This is, imagine this is the degree sequence of our GMP, right? In GMP, most of the vertices, maybe their degree should be n times p. This is expected degree, right? Most of the vertices is here. But there is some bad set. This is our S, right? There is some vertices of low degree S, okay? And there could be some high degree vertices up here as well. You could have some large degree vertices. Maybe I should use a different color. Okay, maybe you have some large degree vertices. So all you need to do is that you keep the low degree vertices, you keep their degree, so that you don't increase capital X, the random variable. Because when you do the sparsening, you don't want to increase the number of vertices of degree at most 1. Those you have to delete anyway. You have to. So we don't want to increase the number of vertices we have to delete to get H. So you have to keep low degree vertices. But since they are low degree, they are sparse also. They don't cause too much trouble. But for this blue part, you squeeze it down, you smear it, meaning that you take a random subset of its edge set to make it sparse. And that's the idea, okay? I don't know what else to write. Let me just write a few lines here to make it rigorous. So basically, we sparse and G. So what we do is you do two things. One is you take a random slice, G1, which is Gn, what I'm writing here, MP over 10 to the 6. I wrote something wrong there, P 10 to the 6, okay? So instead of taking GMP itself, we're sparsening it by 10 to the 6. This is the sparsening part. But as I said, this random slice is sparse, that's good. But we might increase X and Y, right? So we need to keep the low degree vertices. Then second one is to keep X from increasing. We don't want capital S to go up. So this is to take G0 or G2. Take G2 to be a subgraph of G and P such that you just take some okay. If its degree is larger than MP over 10 to the 6, you just take MP over 10 to the 6, you smear it down. If degree is fall below that, that means it's in capital S, then we take all its edges, all right? We don't want to increase capital S. So at the end, you take the union of these two. G0 itself is sparse, and it has all the pseudo-random property because of the first random slice. You take the positive proportion of the edges, you have all the large set expansion property, upper uniformity, just that the second deterministic part, G2, is to keep X from increasing, okay? Then you apply 414 on this G0, that's it, okay? And there's some other corresponding propositions for the, you have to check that the blue box here, the G1, satisfy the upper uniformity and large set expansion. That's by proposition 418. And standard thing here, okay? Not so hard. That's a sketch of the proof. I hope that's intuitive. The details are not that important, I think. Okay? The whole purpose here is to make it sparse without increasing low degree vertices. Then, yeah. All right, so I will stop here. The key thing we learned today is this one. Okay, which then give us the best possible improvement here. So all these already give 422, the result by Alan Fries. To prove 423, basically we have the first and last 0 and 1 statement, e to the negative c, this thing. Just use what we have proved, the sparse expander and things, blah, blah, blah. Then you reduce this e to the negative c. This is exactly the probability that the minimum degree of GMP becomes at least 2. So you just need to verify that. if this probability, this is the probability, okay? We need to verify that this is the probability that GMP has minimum degree at least 2. And this is also a basic thing to check. So if you check that, combined with what we have proved, it gives 423. Okay. So tomorrow we will start trees, boundary degree trees. This will be all for cycles. Maybe we have a couple minutes for questions if you have any.
No one has questions? And then let's end the lecture here today, and then we can meet again tomorrow.
Okay. See you.
And thank you for the full lecture.
Oh, are you in England or is it?
Huh?